Hi guys, I hope you all had a nice weekend. Today's lesson, we are going to continue working with these conditional trig equations, but we're just basically going to be doing more practice. And so I'm just going to be doing a variety of different examples with you, and then just want you to continue with the part 3 homework assigned in the packet. So for this first problem, there's actually two different ways to go about solving it. I'm going to show you both ways. It really just depends on what you see first, how you choose to solve the equation first. And so in this case, we have 1 minus cosine x over sine x equals 1. So a lot of you guys might be thinking to maybe get rid of the fraction and multiply through by sine x. So that's definitely one way we can work through with the problem. So I'm going to go ahead and do that. Just get my pen working here. And so what's tough about this step is that it kind of leaves us a little stuck, because remember I said before that sine and cosine are your basic trig functions. There's no real identities for them. So in order to sort of get them to an identity, the strategy would then be to square both sides of the equation. And I want you guys to star this step, because anytime we square both sides of an equation, it's guaranteed that at the end of the problem, we're going to end up with extraneous solutions that don't work. So we have to check our work when we go back. So I'm going to just FOIL the left side out. So we would get 1 minus 2 cosine x plus cosine squared x equals sine squared x. And then the idea here is that because of this cosine x, again, there's no real identity for that, right? And kind of like everything on this side is in terms of cosine, I can use the Pythagorean identity for sine squared x to get it to be in terms of cosine x. So it would be 1 minus 2 cosine x plus cosine squared x equals 1 minus cosine squared x. So then I'm going to move all this stuff over to the left-hand side. So subtract the 1 and add the cosine squared x. And so far, that the 1's will cancel, right? This gives me 2 cosine squared x minus 2 cosine x equals 0. And then we would look and see like how we would factor this. So you might notice that there's a GCF of 2 cosine x. So I'm going to take that out. I'd be left with cosine x minus 1. And then you just set each factor equal to 0 and solve. So here we would divide by 2. And obviously 0 divided by 2 is 0. So this is where cosine x equals 0. So obviously we have to be on our axes, right? And since it's cosine, that's your x component when you're on the axes, which is here and here, which means x is going to be pi over 2 and 3 pi over 2, because remember, we have to always stay between 0 and 2 pi. That domain will never change for any of these problems. And where cosine x equals 1, in fact, that is on the axes as well, but that's right over here at x equals 0, okay? But don't be so quick to box all your answers, because remember we had taken the step where we had squared both sides of the equation. So we don't really want to just box our answers and that's it. We need to check our work here. So in order to check your work, I'm going to sort of walk you through how to do this. We can absolutely do this manually, right? So here would be the check. And we'll just kind of go through and do one at a time, right? So suppose we're checking when x equals pi over 2. I'm just going to plug it into the original. So I'm going to do 1 minus cosine of pi over 2 all over sine of pi over 2. And I'm hoping that that will end up equaling 1, right? We want that to be a true statement in the end. Well, cosine of pi over 2, that's just 0. So we get 1 minus 0. And sine of pi over 2 is 1. And we know 1 over 1 is 1. So that's good. That answer works. Okay, so I'm going to box that. And now we're going to check when x equals 3 pi over 2. Again, go back, plug it into the original. So we get 1 minus cosine of 3 pi over 2 all over sine of 3 pi over 2. And we want to know, does that equal 1? So again, cosine of 3 pi over 2 is 0, but sine of 3 pi over 2 is negative 1. So that does not equal 1. So there you go. That's an extraneous solution. It doesn't work. We have to reject that answer. Okay? We're also going to check when x equals 0. Okay, and again, we want to see if this is 1. Well, if I get 0, I get 1 minus cosine of 0. Well, that's 1. Sine of 0 is 0. This is already undefined, so no, that doesn't work. So this is also an extraneous solution. So just x equals pi over 2 is our answer there. So that's definitely one way you could have chosen to do the problem. But if you look at the original problem a little bit more closely, another thing you guys may have noticed about 1 minus cosine x over sine x is that actually one of our identities from Unit 12 applies, right? If you notice, this is one of the half angle identities for tangent. So we can replace this entire left-hand side with just tan of 1/2 x equals 1. And then this becomes like a problem that we did in day 2 stuff where we can let a equal 1/2 x. We're only going half a rotation. And so we would get tan of a equals 1. Okay, so again, tangent's going to be positive in quads 1 and 3. And when tan is 1, we know that's our 45-degree angle, or pi over 4. So that means that a is pi over 4 and 5 pi over 4. And we know that's equal to 1/2 x, because ultimately we want to solve for x. So we would multiply everything by 2. So we get 2 pi over 4 over here, which is really pi over 2. And 10 pi over 4 here, which is really, 10 pi over 4, which is really 5 pi over 2. But keep in mind, because I was noticing in some of the homework you guys didn't take your domain in mind. Again, remember in the end, you always have to stay between 0 and 2 pi. Well, 5 pi over 2 is beyond 2 pi, right? Because if I had a common denominator of 2, 2 pi would be 4 pi over 2. So 5 pi over 2 is going to be over that. So we have to reject this because it's outside the domain. And again, we only get one answer of x equals pi over 2. And then we're done. Okay, so now we'll move on to number 2, which says 1 plus tan x minus secant x equals 0. And I'm going to kind of use a similar strategy to what I did in method 1 for example 1. Is I'm going to move the secant x over to the other side. And because I can't do anything with tan and secant just by themselves, I can do more with them if I square both sides of the equation. But again, I'm going to be careful because squaring both sides of an equation is going to give me an extraneous solution. So I have to check my work here. So I'll FOIL out the left. And the right becomes secant squared x. And again, we can use a Pythagorean identity for secant squared x. Right, so we keep the left the same. And we know that secant squared x is going to be 1 plus tan squared x. That's your Pythagorean identity there. And then I move terms over. So if I move the tan squared x over, that kind of goes away, right? So goodbye. If I move the 1 over, that goes away. And so really, I'm just kind of left with 2 tan x equals 0, which means that tan x equals 0. Okay, so we can solve that. So tan x, remember the ratio for tan when you're on, this is obviously on the axis if it's 0. So that's y over x. So you really want whenever your y is 0. So that's going to be here and here, which are the angles 0 and pi. Okay, But again, we'll do a quick check of our work here. I'm just going to do it quickly over here on the side. Plug into the original problem. So 1 plus tan of, let's say we check when x equals 0 first. So 1 plus tan of 0 minus secant of 0. We want to see if that's equal to 0. So we get 1 plus tan of 0 here is going to be 0 minus secant of 0, that's the reciprocal of cosine. I know cosine there is 1, and the reciprocal of 1 is 1. And that, in fact, does equal 0. So that's good. This is a good answer for us here. We'll box that. And then we want to check when x equals pi. So we get 1 plus tan pi minus secant pi. Is that equal to 0? Well, 1 plus tan of pi over here again is 0. Minus secant of pi, well, cosine there is -1. The reciprocal of -1 is -1. So minus a -1, watch your double negatives there. So that's really 2. So this one does not work. So we have to reject when x equals pi. So just x equals 0 there. Okay. So then we move on to example 3. And in example 3, we have tan to the 4th x minus 2 equals tan squared x plus secant squared x. And again, it looks like we're working mostly in terms of tan. So my eye is going to go to the secant squared x and want to transform that into its Pythagorean identity. So I'm going to go ahead and do that. So I know its Pythagorean identity is tan squared x plus 1. And then I have like terms here that I can combine. So that's 2 tan squared x plus 1. And then this is actually going to turn into a quadratic, right? I have a 4th degree, I have a 2nd degree, and then I have a constant. So I'm going to move stuff over to the left-hand side. So that'll give me tan to the 4th x minus 2 tan squared x. If I subtract the 1 over, that gives me minus 3 equals 0. Okay, so again, this is a quadratic that we need to factor. We need factors of 3 that will add up to -2. So your factors for this should end up being tan squared x minus 3 times tan squared x plus 1 equals 0. And then we set each one of these equal to 0. So this gives us tan squared x equals 3. And I'll just work vertically here, and then I'll come back over here. So you want to isolate the trig function by itself here. So I have to square root both sides of my equation here. But again, don't forget plus or minus when you do that. So you get tan x equals plus or minus root 3, which means since we're plus and minus, we have to be in all 4 quadrants. And root 3 makes me think of my 30, 60, 90 triangle. So which angle, when you take opposite over adjacent, gives me root 3? That's going to be my 60 degrees, which I know is pi over 3. Okay, so my answers there, since I'm in all 4 quadrants, I got pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay, coming back up to this side over here, we would get tan squared x equals -1 if I were to set that equal to 0 and move the 1 over. So this time, when I go to square root both sides of my equation, well, square root of -1, that becomes I. If you get imaginary, your answer there is just no solution. It's not going to yield any answers here. So because my original equation, you do have to check when your original equation is in terms of anything but sine or cosine. You do need to check your answers, but you could do this kind of quickly mentally because the idea is that tan and secant, they actually have denominators, right? Tan is sine over cosine and secant is 1 over cosine. So we never ever want our denominators to be equal to 0. So I always have to make sure that the answers that I got won't make, basically in this case, cosine equal to 0. And because they were all 60-degree angles of some sort, I know cosine of 60 is not 0. So all of these answers would work. Okay, so that's how you can kind of do a quick check sometimes. Okay, then we have one last example here. Says cosine 2x tan x equals cosine 2x. And again, some of you guys might be tempted to divide through by the cosine 2x, but remember, we don't ever want to divide through by our variable. So instead, I'm going to subtract over this cosine 2x from both sides to give us cosine 2x tan x minus cosine 2x equals 0. And then the cosine 2x ends up becoming a GCF. So I'm going to take it out. I would be left with tan x minus 1. And then you just set each factor equal to 0 and you solve. So this would be equal to 1. Okay, so now for the cosine 2x equals 0, again, I have a double angle there. So I'm going to go ahead and let a equal 2x. So I can just solve cosine of a equals 0. And again, cosine is equal to 0 up here and down here, which means a is going to be pi over 2 and 3 pi over 2. But because it's 2x, that means I went around the circle another full rotation and landed at those same angles. So I have to add 2 pi to each of those angle measures, right? So this is just the first rotation over here. So now the second rotation, if I do 4 pi over 2, which is 2 pi, right? So 4 pi over 2 plus 1 pi over 2 gives me 5 pi over 2. And 4 pi over 2 plus 3 pi over 2 gives me 7 pi over 2. This would be my second rotation. And again, this is all equal to 2x. We don't want 2x, we want 1x, so I'm going to multiply everything through by 1/2. So we get pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, and then over here, we're just solving when tan x equals 1. Again, that's where tan is positive, so that's quad 1 and 3. And I already know this is my 45, 45, 90 triangle, so my reference angle is pi over 4, which means x is pi over 4 and 5 pi over 4. But again, those are kind of redundant answers from what I got here, so you don't have to write them down twice. It's okay to just write it down once. But because my original had a tan in it, remember tan is sine over cosine, so I do want to make sure that none of these answers give me that cosine is 0, but in fact it's not 0, right? Cosine x is not 0 because these are all 45-degree angles, and we know cosine of 45 is not 0. So these are all acceptable answers. Okay, so I hope that gave you guys a few more strategies on how to solve these equations. I know that they're not the easiest because they have some nuances to them that you have to pay attention. So just do your best with the homework, and I'll check back in with you guys on Wednesday. Thanks.